Thank you to the organizers. Thank you all for coming. This is going to be a bit of a change of pace. I'm definitely not energy humanities. I'm not really much of a historian, but I kind of fake a historian as a geographer. So I'm interested in oil prospecting. I'm going to talk a little bit about some portions of my dissertation, trying to synthesize it into this presentation. I start with this picture. I like it a lot. I think it's very evocative of what I'm interested in. These are the hands of a man named Anders Robinson, who is a very famous 20th century geophysicist. And what he's most famous for is developing a certain algorithm in the 1950s called deconvolution. And he does so in order to help oil companies resolve seismic data that they were collecting off the shores of the Gulf Coast, which was too noisy and therefore not usable. And so he develops this algorithm in order to resolve that noise. And this algorithm, for those who don't know, is a very important, subsequently very important just a sort of underlying filter that is used in signals processing, digital signals processing, across a wide context of different applications. And so this image is very interesting to me because I'm interested in this antagonism between intellectual and manual labor. And of course, and again, Marxists in the room know, it's a very important aspect of a lot of that literature is thinking about the extent to which intellectual labor becomes alienated from manual laborers within the production process, first gets abstracted and objectified in terms of routines and in terms of instructions and protocols, and eventually those get objectified into machines from which the labor, the body labor becomes an appendage, as Marx says. And so that's a very important history, but one thing I'm interested in is the extent to which the intellectual labors are still always embodied as well. And so thinking about literally like Anders Robinson working with his hands in order to first hand digitize these seismic traces in order to develop this algorithm that he eventually feeds into the first computer at MIT, the whirlwinds. And so this has me thinking about this concept of practical abstractions. And I mean practical abstractions in two different ways. On the one hand, abstractions of practice and a sort of Marxian sense of real abstractions. So not thinking about abstractions as mentalizations, but as already embodied in our practices, in our relationships. And then on the other hand, thinking about practical abstractions as abstractions which are pragmatic, which are context dependent. There's a kind of consciousness of their status as a heuristic, as opposed to some sort of a priori deductive universal law or principle. And so this brings me especially to industrial sciences, because industrial sciences are very much governed or guided by these practical abstractions, which are only valid insofar as they work. So what I'm going to be talking about is this portion of my dissertation project, which tries to reconstruct the history of industrial geophysics as this extremely formative and influential data science. This data science, which is also highly dependent on these practical engagements between oil prospectors and the earth. And then through which I want to suggest a particular epistemological form of the subsurface emerges. And so I'm writing against, on the one hand, this false antithesis between extraction and abstraction, digital abstraction. So extraction industries have this notoriety of being sort of crude or rudimentary or reactionary, and then the IT industry is supposed to be progressive and futuristic. And so thinking about exploration geophysics and its application, especially in the oil industry, as highly technologically sophisticated, and it has been for a long time, and also very formative for digital technology. And so I'm also thinking about this as writing, a history from the perspective of the present, and there's lots of good work in media materialism and geography and political ecology on AI data centers and the materiality of that process and the importance of these huge amounts of energy and material throughput as a condition of their existence. And all of that is very important, and I'm trying to approach it from a different perspective, which is to ask, to what extent are these digital abstractions already implying or presupposing a particular extractive relationship to the earth epistemologically? So in other words, is there a relationship between how knowledge is produced via digital technologies and these practical engagements with the earth that are premised on exploration and production of oil? And a lot of this, the empirical side of this, is not really what I'm going to be talking about, but you'll have to take my word for it. There's quite a bit of convergence between geophysics, academia, the oil industry, and also the military in the 1950s and there's this very interesting industrial history that I think supports the arguments. But what I'm going to be talking about today is the sort of conceptualist side and thinking again about filters as filters develop within the oil prospecting business. Because I think that, for me, that is like what is very formative or what is prefiguring a lot of the digital technologies in the mid-century. And to give a little bit of a theoretical orientation, this has turned me to critique of the political economy of science, which I understand is this sort of marginal but resurgent corner of science and technology studies. So I'm interested in like 70s, 80s radical science movements across Italy and the UK and the US, Science for the People magazine, which has recently been rebooted. And thinking about it, what's fascinating to me about that literature is that it's actually coming from scientists themselves and not like people like me or humanities. And it's in the period of like politicizing scientific work and scientific labor in the 1970s, 1980s. So that's one aspect. And then the other aspect is this sort of materialist history of science, which goes back to the 1930s, Boris Hessen and the Soviet delegates at the Second International Conference for the History of Science and Technology in London. And they're asking these, at the time, very controversial questions about to what extent do the social and economic context of the scientific revolution matter for the kinds of knowledge that's being produced at the time. And so just the gist of it, what I really like about both of these sides of literature is thinking about science as a particular kind of labor, which is to say that it implies particular means of production. And then there's a lot of inquiry, historical inquiry into how those means of production or scientific instruments are produced. So that's the sort of orienting, theoretically orienting basis of a lot of my work. And then also, yeah, as it's been picked up by people at the Max Planck Institute, this concept of historical epistemology, thinking about the dynamic relationship between cognitive structures as they develop in and through particular tools and instruments. Yeah, so different sort of conventions for presentation, but these are the research questions that have been guiding the dissertation, and afterwards thinking about, as I turn it to a book project, just how do oil prospectors produce knowledge about the subsurface? How have the associated means of knowledge production helped transform these cognitive structures in geophysics? To what extent does this industrial geophysical reason influence early digital algorithms in the 1950s? And then more recently, I've been thinking about this sort of critique of science within the field of Marxism and how this particular epistemological form, which is emergent at this time, helps capital overcome barriers to exploration and production of oil. Okay, so to understand this new form of thinking and knowledge production about the subsurface, we have to go back to the 1920s. In the 1920s, geology is being applied. It's been applied for several decades prior, but it's sort of coming to the end of its resources, which is to say that all of the geological surveys have explored the continental US, and any sort of superficial anomaly which would motivate further investigation and further drilling has been exhausted. And so in the 1920s, there's this huge crisis of scientific prospecting. Plain geology, as the very famous oil man Everett Lee de Goyer says, was coming to the end of its resources. And so as a result, you have this huge explosion of different experimental techniques for oil prospecting in the 1920s. You have a bunch of quack scientists who are going out and sort of shilling their services with very dubious technologies. Divining rods makes a new sort of resurgent appearance in the oil fields. Paleomicrobiology becomes very important for the study of like drill cuttings and core samples. And then most importantly, geophysics and applied geophysics or exploration geophysics. And I don't have too much time to get into it, but you'll have to take my word for it that exploration seismography becomes the sort of bedrock of geophysical exploration for a variety of different reasons. But in order to explain this sort of evolution of filters from early geophysics, early exploration geophysics to the 1950s, we do have to have a bit of an understanding of how exactly exploration seismography works. So in a nutshell, what they used to do back in the day, you'd have a seismic crew and they would go out into the middle of the field, they would blow up a bunch of dynamite that would create a mini earthquake which would propagate underground. As it propagates underground, it interacts with all sorts of features in the subsurface which affect the wavefront as it's expanding. and it affects its shape, it affects its velocity, and those things are eventually picked up when that earthquake makes its way back up to the surface. And from that information that's recorded at the surface, you can, loosely speaking, reconstruct the geometry of the subsurface. And this image is somewhat helpful. I like it both because it's an illustrative sort of pedagogical tool to think about this explosion of dynamite, and then you see these ray paths that are going underground, and they're bouncing off things, and they're making their way back to the surface, and that's like the image that's reconstructed. On the other hand, it's not actually how any of this works because it's so oversimplified. Like no portion of the subsurface actually looks like that. The ray paths are never that clean. Nevertheless, hopefully that gives a kind of idea of what's happening. And the other thing to mention too about exploration seismography is that it's not finding oil directly, but it's finding structures. It's trying to reconstruct the geometry of the subsurface in order to identify that geometry with regions that are likely to bear oil. And so this becomes very important in the US Gulf Coast because of this very specific geological formation, which is quite rare actually on the shallow surface of the earth, these huge salt domes that exist in the Gulf Coast. And what's interesting about these salt domes is that, again, like I said, the geological surveying has been exhaustively explored. They don't have a very significant presence at the surface. They're more or less undetectable. Most of them are. Nevertheless, as an oil historian says, they're geophysically conspicuous right beneath the surface, which is to say that they have very high contrast with surrounding country rock. And this is especially true for seismography. There's a high seismic contrast between the salt domes and the surrounding country rock. In other words, as the seismic wave propagates underground, it speeds up much, much quicker as it passes through the salt dome. In some places in the US Gulf Coast, like twice as fast. So it becomes a very clear signal on the seismic record. And so the search for more oil in the US Gulf Coast essentially becomes a search for more salt domes. But what's interesting about this period is they're all sort of like fascinated by the quality of these records that they're producing. And so there's a lot of like exuberant praise for exploration seismography and geophysics in general. De Goyer talks about it as if they're the divining rods of the modern prospector. Another oil man, Donald Barton, hails them as brilliant, almost to the point of clairvoyance. But by the end of the decade, new limitations are very quickly setting in. For one, again, thinking about what seismographs actually do, they're identifying structures. Not all salt domes bear oil. And then on the other hand, not all oil regions are so clearly geophysically detected. And at the surface too, there's all sorts of complications that emerge. Again, thinking about like the actual practice of exploration seismography, there's only so many places in the US that you can blow up a bunch of dynamite without pissing off a bunch of people. So it's in rural, very sparsely populated areas where this is most routinely applied. And so you're leaving off quite a bit of the country if you're only looking at those places, and also flat land that's easy to haul all these instruments to, things like that. If you've read Jeffrey Bowker's work, I mean, he's the king on that stuff. But one thing I want to focus on is this specific restraint, which has to do with noise. Because again, thinking about how these signals are filtered at the time. So the earliest filters are all frequency filters, or filters that are prepared in advance in one way or another. And this poses a huge constraint on seismic interpretation because it means you have to effectively already have some sort of sense of what the noise is in order to filter it out. And the problem is, as seismic prospectors quickly discover, in more complex regions, there's other sources of noise that can't be filtered out by knowing about them in advance. And so again, thinking about this actual practice of prospecting, this seismic wave propagates through the subsurface, and if the region is more complex, you have rock beds that warp and bend, you have fault lines that go off, you have not sharp discontinuities between rock beds. All of these things make the subsequent seismic record uninterpretable. And so there's this big problem of how do you filter out the noise in order to determine the signal within exploration seismography. And I just want to focus on one very, I think, illuminating example of this comes from this guy, Frank Reiber, who is a Californian inventor. And again, he's far away from a lot of the geophysical activity which is occurring in the US Gulf Coast. And he's trying to prospect for oil in California, in the San Joaquin Valley, in very complex subsurface regions. And so he's noticing this problem of what they call multiples, which is to say, as the seismic wave propagates underground and it breaks apart, the wavefront breaks apart, and then it overlaps against itself at various points along the line. So you create like destructive and constructive interference. You create more noise on the basis of how the travel path of the seismic wave. And so he's identifying this, and he constructs this entire machine to try to attenuate this problem, essentially by controlling for the direction of the incoming portion of the wave at the geophone or the seismograph. And it gets complicated exactly how that works, but the key thing that I want to stress is that prior, you have to anticipate, you have to know in advance what the noise is, and so you have to set up the filters beforehand and then record. But now, with this Geo-Sonograph, you get to iterative filtering. And so what he's doing instead, he's inverting the temporal relationship between filtering and recording of the data. And this becomes a very, very important, I think, reversal, which anticipates a lot of the digital filters and digital algorithms that emerged in the 1950s. It's a different way of thinking about a kind of unpredictable complexity of the subsurface. So as I understand it, in principle, a lot of the scientific applications early on in the 1950s that early modern computing is being used for have to do with thinking about complexity and unpredictability in a different way. So in other words, statistical techniques of data analysis. And so this is already, being recognized in the 1920s, 1930s by not just Reiber, but this is a very illustrated example. And it's in order to resolve this noise, it's contingent upon creating this new method of filtering, which opens up this very different data space, which is produced after the fact, which has a sort of loosened relationship to the actual data that's being recorded in order that you can sort of manipulate that data afterwards. And so it also it gives a new priority for what is actually being captured or surveyed underneath the subsurface. The priority now is to maximize your data collection in order to anticipate that you'll be able to filter out the noise subsequently. And so all of these things are, to me, like very much anticipating digital technologies. So in the time that remains, I just want to try to bring this up to speed to the 1950s. One thing that's important to note, though, is that Reiber is definitely ahead of its time in developing these algorithms. They're far too complicated for oil companies. He goes bankrupt by the end of the 1930s, and he sort of lives his life not realizing that he, in principle, is developing techniques of data analysis that would become standard by like the 1960s, 1970s. Nevertheless, the same sort of problem, because it's inherent to the actual practice of exploration seismography, continues to repeat itself. So this problem of multiples or overlapping waves becomes very a kind of technical constraint on future oil exploration, and especially as it moves further offshore. Because what happens offshore is when you're generating the seismic wave, a lot of the energy of that wave doesn't actually pass underground, but it just bounces around in the water medium. So you create this echoing or distortion on the record, which again is this problem of multiples. So this is the context in which Anders Robbins, who I talked about at the beginning, emerges within this problem of multiples, and then coincident with early modern computing. And so on the one hand, you have this growing problem of seismic interpretation in search of a solution, and then concurrently you have this emerging computing solutions that are in search of industrial and scientific applications. And these converge at MIT under the sort of leadership of Anders Robinson and company and colleagues who start this group called the Geophysical Analysis Group. One thing to know about Robinson is that he is not trained. He starts his PhD program in geophysics, but he is trained as a mathematician. He has a master's in economics, and he is very famously a sort of protege of Norbert Wiener. And so his solution to this problem is the adoption of filtering techniques that Norbert Wiener was working on in the preceding period and applying them to this problem of multiples. okay, this may or not be useful. It's hard to explain, but just very like high level deconvolution between these two graphs. So this bottom figure is the observed seismic trace. So like the change in amplitude, the vibration of the wave as it passes through the geograph. That's what's actually observed. And part of what Anders Robinson's model is conceptualizing about the subsurface is that this wave is actually the convolution of all of these little wavelets. So it's like blurring them all together. And so what his deconvolution filter tries to do is reconstruct that to the best of its ability and then compare expected to predicted or expected to observed output. And the difference between those is now understood as the actual impulse, like where those impulses are being generated, which is then associated with different reflecting horizons or the interfaces between rock beds. That, I don't know, probably didn't make much sense. But the point is, a lot of the same principles that motivates Frank Reiber to develop this machine in the 1930s are the same principles that apply to deconvolution. And so the same sort of problem of like creating this data space, having iterative filters, all of these things are anticipated by virtue of just the actual practice of exploration seismography. And then they come to inform deconvolution in the 1950s. Or at least that's my argument. I'll just end here. Again, I've been thinking more about what this really has to do with value and value production. Obviously, on one hand, all of this is being done in order to help oil companies find more oil. And I've been thinking about this relationship between the value form and different forms of measure. Again, thinking about like this difference between intellectual and manual labor. So Pasquinelli has a lot of really interesting work about the development of forms of measure as they become to be objectified within particular control technologies within the labor process. And I've been trying to think about that analogously with a kind of control of the earth on the basis of these statistical measures that are emerging in the 1950s. And so, yeah, I'll just leave with this. One thing that I'm really trying to stress is that there's different kinds of abstractions, there's different kinds of formalisms, and not to sort of confuse them all together, and to think very specifically about like, why is statistical abstraction so significant in the 1940s, 1950s, as it feeds into, in my opinion, like my kind of crank opinion, essentially every aspect of the university, including like humanities, including everything from systems theory to post-structuralism. Again, this is like sort of crank. My crank take can be sort of can be connected back to this period. And so I think that's where I'll leave it. Thank you.